Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the most famous continuous distribution, the Gaussian distribution. We're going to define the Gaussian distribution, then we're going to discuss its properties, and then we're going to apply it to some real-world data. Let's get to it. So why is the Gaussian distribution the most famous distribution, the most widely applied? Well, it turns out that if you have some uncertain quantities that are independent and fluctuate independently, and you add them up together, then they're going to tend to have a Gaussian distribution. And because of that, many naturally occurring phenomena tend to have a Gaussian distribution because sums of independent uncertain quantities are approximately Gaussian. We're going to talk much more about this when we discuss the central limit theorem, but for now, maybe take my word for it. All right, so a Gaussian or a normal parametric PDF with mean mu and standard deviation sigma looks like this. It's the exponential of a squared quantity that is centered at mu, at this parameter mu, and then it's scaled by this parameter sigma. So it turns out that this parameter mu has an interpretation in terms of probabilities as the mean of the distribution, which you can think of as the average of the random variable, the average value. We will talk about means much more later on. And the standard deviation parameter sigma has an interpretation in terms of the average deviation from this mean. Okay, you can think of the mean as the center of the distribution and sigma as quantifying how often, how much the random variable deviates from that center. We will talk much more about means and standard deviations later on. For now, you can just think of them as parameters that determine the shape of the distribution. So let's take a look at a picture. Mu tells us where the distribution is centered. Here it's centered at 3, and sigma tells us how much how much density there is far or close to the center, how fat or thin the distribution is. In this case, the PDF is, in this case, sigma is equal to 1. If we increase sigma, then the PDF becomes fatter. See that the height becomes smaller, like the PDF also becomes shorter because it has to integrate to 1. And if we change mu, we change where the PDF is centered. So here it's centered at -2. In this case, we're centering the PDF at 0, and we're making it even fatter and hence shorter. Sigma is equal to 4 as opposed to 2. Okay, so hopefully that gives you an intuitive idea of how the parameters mu and sigma determine the shape of a Gaussian. And of course, when we're fitting them to data, we have to fit both of the parameters so that we can approximate the data as well as possible. We're going to learn how to do that with using maximum likelihood in the following video. A very important property of the Gaussian distribution is that when you scale it and you shift it, it remains Gaussian. In order to illustrate this, we're going to consider a standard Gaussian. What's a standard Gaussian? A standard Gaussian is a Gaussian which has mean parameter 0 and standard deviation parameter equal to 1. And now we're going to take that standard Gaussian and we're going to multiply it by some constant and add another constant. Okay, this sigma and mu are constants. Remember, every time you see something that has a squiggly line on top, this tilde, it means that it's a random variable. It's an uncertain quantity. We can describe it using the PDF. These other quantities are deterministic. You could just replace them by a single number. So here, for example, we might want to set mu to 3 and sigma to 23, for example, in case that's helpful. All right, so now we want to derive the distribution of B, of this random variable. We do what we always do. We start with the CDF because it has a very nice interpretation in terms of probabilities. What is by definition the CDF of this random variable at B? It's a probability that the random variable is smaller than that particular value. And now we know what the random variable is equal to in terms of this other random variable from which we know the distribution. So we plug it in. We're interested in this event, which is that sigma A plus epsilon, I don't know where that came from, plus mu is more or equal to B. That's what we want. Now we can express this easily in terms of the CDF of this random variable a by moving things around. Here we're assuming that sigma is positive. So we could just say that this is the CDF of the random variable that we know at b minus mu divided by sigma. But it turns out that for Gaussians, we don't have a closed form CDF. We define them directly through the density. So what we're going to do is we're going to use the density and we're going to integrate over the event of interest. So we're going to integrate from minus infinity to b minus mu divided by sigma. Remember, these are all constants. Okay, perfect. So now what I'm really interested in is the PDF of b. So how do I get the PDF from the CDF? I just differentiate. So if you remember your calculus, essentially what's going to happen, we're going to get this guy, because we're integrating up to a certain point that depends on what we're differentiating with respect to b. This is what I'm getting at. We're differentiating with respect to b, and the only b that we see is here. So what is the derivative of this expression? It's whatever is inside here, evaluated at b minus mu sigma over sigma. And now we also have to multiply by the derivative of this with respect to b. So this is where this sigma comes from. But at the end of the day, basically here, we're differentiating it. So if that confuses you, maybe check derivatives a little bit. But we're just taking a derivative. And what we obtain, the result we obtain, is that this is exactly a Gaussian with parameter mu and sigma. We started with a Gaussian with mean 0 and standard deviation 1. If we add a constant, then we shift the distribution by that constant. And if we multiply the random variable by a certain constant, we're making it fatter or thinner by exactly that ratio. Okay, so now I'm going to tell you a little anecdote. So for, I think it was like 3 or 4 years, I used to, do this in class. I would be like, yeah, okay, like this is the Gaussian, these are the properties of the Gaussian. And in general, the philosophy of this course is that we try to always show you whatever we're talking about on real data, so that you see that what we're talking about is useful. So I used to do this, and I would say, oh, now we're going to look at some real data, the height of 25,000 people, and I would show them this histogram, and I would show them the Gaussian fit, and I would be like, isn't this amazing? Isn't this amazing because of the central limit theorem? Height depends on different factors. They're independent fluctuations. This is Gaussian. Wow, I like, the magic of probability. Well, as it turns out, I think this was last year, I went back to this data set because, I was reorganizing my materials and redoing some plots and stuff. And to my horror, I saw that these data were simulated to be Gaussian. So for 2 years, I was telling people like, look, amazing, the Gaussian distribution is amazing. It really occurs in practice using simulated data. So, I don't know. If one of my old students sees this, I hope they get a good chuckle out of this. Anyways, I did find a data set which gives us the height in a population of soldiers. And I did do a Gaussian fit, and luckily, we get a very good fit for this data also. So it is true that the Gaussian distribution is actually really good to model height, because height depends on all of these independent factors. And luckily now I'm pretty sure that these are real data. So I'm not misleading you like I misled my poor students, for unknowingly at least, for a couple of years. Okay, so here you see that we have fit sigma and mu so that they fit the data as well as possible. We will see how to do this using maximum likelihood in the following video. But the point is that this data, you can see the normalized histogram, which is this non-parametric estimator of the density on top of the Gaussian fit. The Gaussian fit is actually really, really good here. So clearly, the assumptions underlying the Gaussian distribution, which is that height depends on independent factors that get added up, clearly hold for this data. All right, so what have we learned? We have learned the definition of the Gaussian distribution, some of its properties, that it actually allows us to fit real data very well, and that you should be careful when you download a data set from the internet, because it might not be what you expect it to be. Thank you very much.